Good evening. Welcome. It's wonderful to have you here. This is the Our Universe Revealed lecture series. My name's Deb Marr. I'm a professor of ecology at Indiana University South Bend, and I'll be serving as the moderator for tonight's talk. If this is your first, is this your first time here? How many? Ooh, lovely. It's so good to see you. Well, let me tell you about this series. We cover talks in all areas of science. This year, we're actually adding in talks in music and the arts, so broadening out. We feature current research and an opportunity to be curious about ourselves, the Earth, and then, of course, today we're thinking about outer space, so going way beyond. This is a partnership between IU South Bend, University of Notre Dame, and the St. Joseph County Public Library. And our goal is to just make really cool information available to the public, and it's been a lot of fun. So without further ado, tonight we are going to be thinking about eclipses, and it's my pleasure to introduce Keith Davis. He completed a Bachelor of Science in Applied Mathematics at the University of Tulsa and a PhD in Physics at Clemson University. He is an associate professor of practice in the Department of Physics and Astronomy at the University of Notre Dame. He's also the director of the Digital Visualization Theater. And this is an amazing facility that provides an immersive experience in high-resolution, high-fidelity images that are projected on a 50-foot dome. And you can use this to examine the inside of complex molecules, such as DNA. You can look at it to look at the internal structure of the human body. And then, of course, it can take you into outer space. So their motto is, "The sky is no limit when it comes to learning." So anyway, it sounded super cool. And so tonight, Keith will be talking about the eclipse that's coming up next week, and solar eclipses in general. So with that, I will turn it over.
Okay, thank you very much for coming. I'm very excited to be here. This will be the first presentation to the public I've given not in the planetarium in a very, very long time. So hopefully I've found a way to do some of the visuals that I would normally have at my fingertips with Keynote or PowerPoint or whatever version of things I'm presenting right now. As was mentioned earlier, we do have 2 eclipses in the next several months coming up. The first will be an annular eclipse on October 14th, and the next will be on April 8th. That will be total for parts of Indiana, sadly not here. But when I think about what I want people to know about eclipses, there's quite a lot. One of those things is safety, obviously, so we will focus on that. We also, I believe, have some eclipse glasses that we've presented that you are welcome to take home with you today. So we'll be passing that out at the end of the presentation. But I want to go ahead and get started. I've got a lot to go through, but what we're going to do tonight is focus on what makes eclipses happen. And I want to start to build in your mind a way that you can answer your own questions about eclipses, because I think that's a really valuable thing. So get ready for the total solar eclipse of 2024. This is my talk today. What we're going to do, that didn't show up the right size. They're outlined at the top, so that's fun. We'll see what other surprises. This is presentation started in Google Slides, moved to PowerPoint, and now it's in Keynote. So we could have some unexpected surprises here, but that's all right. So the first thing we're going to do is review the basic facts of the 2 eclipses that we will be having locally in the next year. And then I want to work on your personal mental model of eclipses, and I'm going to explain what I mean by that. And then we will end with some more details and a reiteration of how to view eclipses safely. So October 14th, there's a lot on this screen, but if you will follow me over here, this background map is a map I got from a website I highly recommend for looking at maps of things related to what you can see from Earth, whether eclipses or any other astronomical phenomenon, called timeanddate.com. They have a very humble name. Their stuff is great, and I highly recommend it. So this map here, you can see this dark line. This will be the path that it takes. This is the darkest part of the eclipse. A little further out, you can see, so this is up to about 90%. This one doesn't quite get to 100%. That's what this color is. This color here gets us, I believe, around 40. And then anything larger than 0% coverage, that's the percentage I'm referring to here, would be this color here. If we zoom in on the region around Indiana, you can see that we are pretty much in the 40% area. And this is an image of roughly the coverage you will see, where this would be the dark side of the moon here, and this, of course, is the surface of the sun. That's going to be about 1 p.m. I had not initially planned to do a lot of events for that eclipse until I looked at our football schedule and I realized that it was the USC game. So that's what I've been doing for the last several months. If you do happen to be on campus, we will have solar telescopes with proper filters set up and some more eclipse glasses to give away. If you would like to come view the telescope with us, if you know campus at all and you know where Jordan Hall is, the DVT is right on the northern end of Jordan Hall. We will be right to the north of that so that people hopefully walking by will see us there. But we will have some events that are open to anybody that can get to campus that day. So that's also for locally, that will start at about 11:39 a.m. Its maximum will be about 1 p.m. and the eclipse will end at about 2:24 p.m. Pretty convenient timing, except for it eats up your lunch, but other than that. The April 8th path, now this is the big one. I recently had a friend text me and say, hey, I just realized there's a total eclipse on April 8th. It's not that far north of my house. Do you want to come visit? I've been talking about this eclipse for 2 years. Where have you been? All right, this is April 8th. So we've got, again, this does reach totality. Sadly, not quite in South Bend, but it does reach totality. That is that center line. And then you can map the colors to the rest of that darkness as well. You may be wondering why we have these eclipse paths are these strange zigzag shape, and that's for 2 reasons. One, this is a flat version of a curved surface. Despite what you read on the internet, the Earth is in fact pretty round. So you can't really get it. That's why you get these strange curves, but if you wrap it, it looks a little more straight. The other issue, of course, is that we are not tracking a physical object. We are tracking how the projection of the shadow of that object maps onto a curved object. So that can make curves seem magically weird, right? So that's what we've got there. And then this will be the coverage here. I think this projector is good enough that you can see that little sliver. Is that clear? Okay, that's about 3% of what we call the photosphere of the sun. The photosphere of the sun is the region that as you go away from the center of the sun, the density of the sun drops, right? It's densest at the core. And for most of the sun, light can't really travel. It gets emitted because it's hot, but it doesn't really go very far. The photosphere is that region of the sun where suddenly the density is low enough that light can kind of travel and really get out into space and eventually reach your eye. You don't want it to reach your eye. You want it to bounce off of something before it reaches your eye, otherwise it will damage your eye. So the photosphere, if any part of the photosphere is visible, it is not safe to remove your eclipse glasses. Hopefully everyone knows that, but I'm going to repeatedly say that just to make sure nobody misses it. I have read stories from ophthalmologists that say, yes, I can see the curvature of the scar, that little crescent in the back of people's eye if they look. So it's a real thing. People sometimes ask me, why is the light suddenly so dangerous during an eclipse? That is a misunderstanding of our warnings. Our warnings are because you don't want to look at the sun when it's not an eclipse, so you're not going to damage your eye on a normal day. Also, the full brightness of the sun, your eye is going to respond to. But when that brightness is dropped down to about 3% its normal, your eye isn't going to fight you about looking at the sun, right? It's not going to water as much, it's not going to constrict quite as much, it's not going to make you look away, it won't hurt as much. So it's not that it's more dangerous than normal, it's just that you're incentivized to look during an eclipse. So again, you will not be able to do that here. However, Oh, also the timing in South Bend starts at about 1:53 p.m. Maximum is about 3:09 p.m. It ends on 4:23. April 8th is a Monday. It's a normal class day for us at Notre Dame. I checked. It is not the Monday after Easter. Whew, that would have been complicated. So we do have students on campus, and we will be planning some events there as well. However, I am telling everyone not to come to those events because I want you to go to Totality, okay? So this is a map of the state. The region in here is where Totality will occur. The closer you get to the center line, the longer the amount of time of Totality you will experience, okay? Because that's how the timing works, is the closer you are to the middle, the longer an amount of time you get. You will have to look at your specific location to find out what the times of Totality are and how long you have to look without the safety of the Eclipse glasses or other protective equipment. The dark area is Totality there. This is the center line. Please go to Totality. There's absolutely nothing like the joy of catching an event utterly outside your control. The first total eclipse that I got the opportunity to see was August 2017, another great American eclipse. I managed to travel with some friends. We were in Wyoming to see it. Something about the fact that we got lucky to have the resources to travel. We felt fortunate to have friends there with us. We got the chance to actually see, we got the chance to have no clouds in the moment, right? We had clouds in the morning, clouds afterwards, but not on the moment, right? There's something in a day where we can watch anything we want on Netflix. There's something special about when the universe is putting on a show for you, but not really for you, right? Because you can't ask them to reschedule it. So there's something more emotive about that even than just seeing a picture of it. But to give you a little bit of a visual, this is a telescopic image of the sun during a total eclipse. If you look very carefully, you may see the moon. I am not sure, you can check this link, I am not sure if they imposed the actual image of the moon there. Obviously it is the moon there. I'm just not sure if you can capture the detail while you're capturing this. Does anyone know what this wispy material is? Say it again. There might be. Flares are usually something on the surface of the sun. That's a really good guess, though. This is apart from the surface of the sun. We sometimes think of this as the atmosphere of the sun. This is called the solar corona, which is from a word that means crown. The surface of the sun is about 5,800 degrees. This material is millions of degrees. We don't know why. We actually have the Parker Solar Probe occasionally dipping into this region, actually entering the atmosphere of the sun to try to help understand that. I'm not an expert on heliophysics, but I have to mention it. The other thing I'd like you to know is that this material, despite the fact that it is much, much hotter than that surface of the sun, that photosphere, it is very, 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 very low density compared to the photosphere, which is why it doesn't produce enough light to damage your eye. So and I think there might be a touch of photosphere visible here. They're probably selected that moment for dramatic effect because it makes for a good picture. But basically the idea here is this is what you get. This is the beauty that you will get if you get the chance to see a total eclipse. So I highly recommend people to go to Totality.
There's a question.
Yeah.
So that, if you're looking at it without any aid, you would see that corona.
It doesn't quite have this detail, and it looks much smaller on the sky, but yes, you can see that. I can now verify that, having done that. But yeah, it's really quite beautiful. There's some strange illusions in the way the brain understands size of things on the sky. If you've ever noticed, when you look at the moon on the horizon, it seems enormous, and then you look at it overhead. If you actually measure the size it is, it doesn't really change very much, but something about your brain makes it feel bigger on the horizon. People that study illusions are not in agreement on why that is. But this will be really small on the sky, but it will look pretty cool. It's absolutely worth it, yeah. Okay. The next thing I'd like to do is start talking about what I call your mental model of eclipses. And this way of teaching came to me after I had a student, when I was teaching a general astronomy class, I had a student come to me. And in fact, this has happened several times. So they said, I'm really studying hard in your class, but I'm really in trouble. And I said, okay, great. I'm so glad you came to me. Let's talk about it. And one of my first questions is always, how do you study? And more than once, students have said, well, I use flashcards. And my jaw hit the floor. Because the way I teach, there's no way flashcards are going to help you. Because I'm not interested in you memorizing specific pieces of information, particularly in the age of Google, because we can look that up really fast, right? You don't really need to remember the base facts. If you review facts often, they'll just stick automatically, and that's useful. What I want you to do is have an idea of how things in space and the sky are moving so that you can answer your own questions about the eclipse or any other phenomena. Now, I can't teach you all of astronomy tonight, but I can do a couple of pieces on the eclipse. Are we on board for that tonight? Okay. So let's think about our mental model of the eclipse. So first of all, in a solar eclipse, we could say that the moon obscures the sun. So I'd like you to think about, why does the sun dim in that situation? Why is there less light getting to us from the sun? And then think about who could see that eclipse. The next thing I'd like to say is in the lunar eclipse, this is a case in which the moon moves into the Earth's shadow. Why does the moon look dim in this case, and who can see the eclipse? And then I want us to think about shadows. Raise your hand if you have ever heard of the umbra of a shadow. Raise your hand if you have ever heard of the penumbra of a shadow. Would anyone like to give me a definition of umbra? Anybody willing to speak to the public? You don't have to. Yes?
It's like the main darkened part of the shadow.
The main darkest part of the shadow. Is that right? Yeah. So that is the darkest part of the shadow. Okay. That's great. That's the definition I usually find, and honestly, until recently, that's the definition I always gave everybody. I want us to expand that. And you might have been going further, but I cut you off because I'm making a point. All right. So the other key thing I want to say is that mental models affect your understanding. If you learn a mental model, then you can answer any question for yourself, and also you can take in new information more easily if it has a framework to attach to, right? I think that feels fairly instinctive to people. When I was a child, I asked my father a very simple question, or what I thought was a very simple question. I said, hey, Dad, why do earthquakes happen? And he said, well, son, the Earth moves on plates, okay, and the plates bump together, and that makes the Earth shake. Earth sits on plates. It's literally what I thought he was telling me. Plates bump together, Earth shakes. I was no dummy, so I was like, wait. Okay, well, but there's not earthquakes all over Earth at the same time. Why are there earthquakes only? Well, not all the plates move at the same time. Dad just must not know what he's talking about. So, what was the problem in this explanation? The problem in this explanation was he didn't give me the context to understand what he meant by this word, or even this. He may have said the Earth's crust, but he didn't tell me what that meant, right? So I think it's really important that when you feel like you are missing something or don't understand something, interrogate other people's words, the people that are explaining it to you. So hopefully you'll interrogate me tonight during the question and answer. But I really think that that's an important part of this. So I want you to think, for our mental model of eclipses, I want you to think of the solar system as a room with a single light bulb. Yes, there are many billions of light bulbs because they're all the stars, right? But those stars are so very far away that they don't really emit enough light to illuminate much. They're beautiful to look at, but they don't illuminate. So we can think of the solar system as a room with a single light bulb. So that means that every single object in that room or in space around the sun is half lit. 50% of its surface is lit all the time. And every object casts a shadow, okay? Because there are no other sort of sources of light. If it's not facing the sun, it's not getting any light, unless that light is bouncing off of something else, right? On Earth, we have the moon, and it can be in a position that gives us a little light at night. But if you think about this being the Earth here, This would be the lit side. Over here would be the unlit or the nighttime side, right? So people over here aren't getting any daylight. They have to have some other source of light if they need it. All right? So if we want to think about casting shadows, and the advanced students in the room will immediately notice that something is wrong with these shadows, we will get to it. But for now, the simple version works. So the simple version works. So if we have this shadow right here, this is kind of how I want you to think of it. So now let's zoom in on our system. The sun is over here to our right. It is illuminating us from that direction, and our shadows are moving that way. Now, I want to ask you a question. Where do I put the moon to make a solar eclipse happen in this diagram? Yes?
Right in front of the Earth.
Right in front of the Earth, so right here. Yeah. Okay, so let's just remember what I mean is the moon, of course, every month is going to move around the Earth like that. So where do I put it? Exactly right, head of the class. Okay? So the shadow, because it's the shadow of the moon, is casting upon the Earth. If someone is over, now note that the shadow of the moon is smaller than the Earth, right? So if someone is here, can they see, do they know that the eclipse is happening? No, because they're not inside that shadow, right? So there is no obscuration of the sun there. All right? Answer me this, and I'd like everybody to take a second to think about it. If the moon is there in that position necessary to cause an eclipse, what phase is it? Okay, new, right? Okay, the reason it's new, of course, is because we don't observe from top down. We observe from the Earth, and they look to the left, and they see that there is the unlit side of the moon is what they can see right now. Half of the moon is still lit. It's just the half of the moon that we cannot see. So solar eclipses must necessarily happen only on the new moon, right? Pretty obvious and easy to understand, okay? By the way, this is just for funsies. It doesn't really have anything to do with eclipses. If the moon is down there, what phase is that? We always have a broad range of different knowledge in rooms like this, and it's always a lot of fun to see what people will say. As a hint, I'd like to remind you that the person looking at it has to be on this side of the Earth, right? Or maybe over here, but they're kind of going to be upside down. So, and I'm drawing this as though we are viewing from the northern hemisphere, and there's a lot of complications in it, but half of the moon is lit is what the person sees. Because I don't think it showed up. I had a line right here to indicate that this is the way you would cut the moon to answer the question, which half can I see? It's the nearer to the Earth half that I can see, so we cut it right there. And sure, it looks like that kind of leaves a quarter of the moon, right? That's not really what we mean by the quarter moon, but it's an easy way to remember it. And now you can see that this person, once we turn everybody right side up, sees that the right side is lit. Again, this is a little complicated. In fact, the image that I found, there's some tilt to it because you're not on a flat planet. You're on the curved surface of a planet, and it will create some complications. But this is the basic way that I teach students to try to understand this. If this is challenging for you, there's plenty of people that have a really hard time with this kind of three-dimensional thinking, and that's okay. You just have to work on it. Okay. So by the way, so that is first quarter. You may wonder why it's called first quarter. It's because it is a quarter of the way around. So it starts at new moon, and then we go around to a full moon, and then we end that moon at the next new moon. So it's first quarter, and I think somebody did say that. And then we would have full moon here, and then we would have third quarter, because for some reason we don't call this one half moon. We don't call this one half moon. This one's quarter, this one's full. This one's, guys, it just gets worse. The more you learn about astronomy, our way of naming things, the magnitude system is backwards. A bigger number means a dimmer object. We're just, it's a mess. All right, so it comes around and then we get a new moon again, right? But so we've got the different basic phases of the moon. Okay. So of course, in order to have a lunar eclipse, where would I need to put the moon? In what phase would I need to put the moon, now that we know the phases? It would have to be the full moon over here, right? Because that's the only way you're going to get the moon into the Earth's shadow, right? Now, who could see that? What about somebody over here? Could they see it? No. Only the people on the half of the Earth, but a much larger percentage of the population of the Earth. So it's the half of the Earth that faces the moon. And do you see how trying to remember why large numbers of people get lunar eclipses as opposed to solar eclipses, it's a lot easier for me to think about, well, where do I have to put the moon? What has to be happening? Oh yeah, of course, everybody that's on that side of the Earth could see it. So it's a much larger population. And to me, that is the advantage of working in terms of these mental models, instead of just remembering lunars, because you probably think of lunar eclipses as more common than solar eclipses. And it's really, although that is also true, some of that commonality is because larger percentages of the population can see them. And so you're much more likely where you live to be able to see one. All right. Okay, so solar eclipses happen only on the new moon. So the phase is connected, oops, we're jumping back and forth. The phase is connected to what eclipse we're going to have, right? Okay. This is a lot, but bear with me here. This is a map of the year as I see it in my head. For some reason, this line vanished, but January's down here, June and July are up here, and then the moon or the Earth moves around the sun this way. That's what makes the year for me. What I have drawn is on the date of every new moon from July of 2023 all the way around to June of 2024. We just put the dates of the new moons. Does that make sense? You see what I'm doing there? Okay, so we have the moon in a position whereby it could cause or cast its shadow on the Earth every single new moon. If the moon is between the Earth and the sun on every new moon, why don't we get an eclipse every month? This is a question that occurred to me when I was a kid and I was learning about this stuff. And I was like, wait a minute, why don't we have an eclipse every month?
The moon isn't always 0 degrees, and it's because it varies tilt.
Right, so you're in the right ballpark. It is about the tilt of the orbit of the moon. Some of your language implied that it might have different tilts at different times, and for most of our life it doesn't. And that's just a matter of trying to get your words out. So this is an example of how I imagine the moon and the Earth look kind of from the side. If you look at their orbits, this would be the Earth's orbit. This is called the plane of the ecliptic. Does the ecliptic sound familiar? That's why it's called that. It's because the moon has to be on the ecliptic in order for an eclipse to occur. And it's not always on the ecliptic, right? Why is it not always on the ecliptic? The orbit of the moon is tilted by 5 degrees to the plane of the ecliptic. Everybody that has reasonable motion in their arms and a pinky, please hold out your pinky at arm's length. Close one eye. The size of that for most people is about 1 degree. The moon takes up about half a degree on the sky. Do you believe me? Does that seem too small? No? It seems too small to me. I know it. I've tested it. I've walked out and put the moon. I'm like, that's about half my pinky, and it still seems too small. But so the moon is about a half a degree. This tilt is about 5 degrees, so we can fit quite a few moons not quite lining up, right? So we only have a region around that, what we call the node, which is where the orbit of the moon crosses the plane of the ecliptic. So it's a little hard to do on this two-dimensional surface, but imagine you've got a flat tabletop or a plane like this. That's the ecliptic defined by the location of the Earth and the Sun. Then imagine a hoop, put it on the tabletop or on the floor, tilt it by 5 degrees. Where do they intersect? Like one side of the hoop goes above it, one side of the hoop goes below it, and it intersects in 2 places. Those 2 places are called the nodes. That's just the word we have for those things. It's nodes. And you can imagine drawing a line between those nodes, okay? So the nodes are the intersection points. You can draw a line between those. That's called the line of the nodes. Hey, look, we got something right. We named something simply anyway. Now, right here, this moon, is it on a node? This is my test to see if my diagram has been effective. Seems like maybe not. Is this moon, if the moon's right here, this is the orbit of the moon, this is the plane of the ecliptic, this is an unreasonably large sun right here that we're looking by. The Earth would be somewhere on this. Is this on a node? No. The nodes are here, right? So this is actually at an antinode. It's at the complete opposite. Okay. So that would be where the node is. Now if we go back to my view of the year, what I'd like to do is illustrate how the line of nodes behaves over the year, and that's what affects when we can have eclipses. So I'm going to fade it out because there's a lot of busy noise on the screen, and I want to kind of have it in the background but fade it out a little. This right here is I'm going to use to mark the line of the nodes. Keep in mind, this is all kind of a rough sketch just to give an illustration. But we know that on October 14th, the line of the nodes is going to point towards the sun, right? Because we're going to have an eclipse on that day, so the line of nodes must be pointed towards the sun. Now, the line of nodes mostly points in the same direction for long periods of time. As the moon orbits the Earth and as the Earth orbits the sun, the line of the nodes slides around with it, mostly pointing in the same direction. It tilts a little. When did it line back up with the sun? April 8th. Actually, so there is a little bit of width in when we can have an eclipse. It doesn't have to be exactly perfectly, especially for lunar eclipses, because the shadow of the Earth is bigger than the moon. So you've got a larger region. There's actually a lunar eclipse. It's not an exciting one, but technically there's a lunar eclipse in March as well. So this is my introduction to what we call the eclipse seasons. We have seasons for eclipses, twice every year. Sometimes you can squeeze a third in if everything's lined up just right, but for the most part, especially around now, the line of the nodes is merrily moving around, mostly pointing in the same direction. It is not exactly 6 months, it's a little shy of that, and that's because it is actually precessing. The line of nodes is turning a little over time, so it's a little less than exactly 6 months apart. Okay, so what do we have to have an eclipse happen? We have to have the moon in either the new phase or the full phase, depending upon which kind of eclipse we want to have. We have a line of nodes. The line of nodes has to be pointed at the sun, which happens twice a year roughly, right? And then the moon has to be in that phase at the same time that the line of nodes is pointed, right? So we're kind of taking, eclipses could happen anytime. Eclipses could happen during these 2 phases. Eclipses could happen during these 2 phases while the line of nodes, or if those 2 things happen at the same time, and then we can continue to narrow as we were to add perturbations and other details around. There's in fact a very complex cycle that I'm not going to be able to talk about today, but I might show you a fun graph at the end of it. By the way, this is not a perfect diagram. I do not think I quite have the scale right. I am learning a new technique here, but this is my attempt to use a tool called Skyfield, which is a Python library that's open source, free, and publicly available that can use It's an easier way of using the Jet Propulsion Laboratory's kernel files, which are what they use to calculate the motion of space probes. So it's the real stuff, right? Totally free. You just have to know some Python, and there's plenty of free introductory tutorials for that as well. So this is Skyfield. I use JupyterLab and Plotly as well to attempt to plot the locations of all of those new moons. Whereas the blue, sorry, this turned out a lot smaller, but the blue is the sun. I should have colored that yellow. The moon is the red here. It's a new tool. I'm learning how to make it do what I want. But you can see this should be roughly degrees. So we can see that at this time, the moon's about 5 degrees above the sun. We also note that the sun's sitting there right there on the ecliptic, barely moving at all. Whereas the moon gets a little closer and a little closer. On our October 14th, it overlaps, and then it moves down, and then comes back up. It overlaps again in April, and so on. Okay? All right. So this is just my attempt to give you a sense. I think I've got the diameter of the moon and the sun pretty close to right, but this system doesn't do it the way I want it to, so I'm still kind of fighting with it. All right. So the solar system is a room with one light bulb, which is the sun. Okay, so that's some of the things we have to get an eclipse. Now, I mentioned earlier that the October 14th eclipse, I said it was partial here. It is an annular eclipse in other places, meaning that it does not quite get to totality. I'd like to talk about why that is now. So step one was, why do we have eclipses 6 months apart sometimes? Also, keep in mind that we always have eclipses 6 months apart. We're guaranteed to have at least one eclipse, either solar or lunar, during every eclipse season because the moon takes 27 1/3 days to go around the Earth, and the eclipse season is effectively 35 days wide. You're always going to get the moon in the right spot for each eclipse season. It's just that it might be on the other side of the planet, which means you don't get to see it, right? So the eclipses really are a lot more common than we tend to think they are. Okay, so now what's the geometric trick that means that we have an annular eclipse instead of like an actual total eclipse on the 14th? So as we mentioned earlier, and this is a definition I was taught for a really long time, is that the umbra is the darkest part of the shadow. I want to move beyond that because, for one thing, why do shadows have dark parts and non-dark parts? Is that obvious to people? I feel like it's one of those things that feels obvious until you start thinking about it, like, wait, why should that be? So let's talk about why. So first of all, where do you think I should put this moon to put it inside the Earth's shadow? Just somewhere over here, right? Okay. What if I put it up here? Now, obviously, this is not to scale, but what if, can light from this top part of the sun get there? So this isn't perfectly dark, right? So the reason is that the sun is an extended light source. It is not a point light source. Stars are so far away, they're effectively point light sources. We treat them like that mathematically in our telescopes. But the sun is an extended light source, and that's why its shadows have fuzzy parts. So there's that way that you get light from that part of the sun. If I squish things a little together to make the drawing on this screen easier, remember the solar system is a room with a single light bulb. We can draw a line, the light from here can reach across this side, so anything above that can get light from this part of the sun. Anything below that can get light from this part of the sun. If we then extend that out to the rest of it, you get regions where some of the light from the sun is blocked, but not all of it. And you get a region where all of the light of the sun is blocked. And it's just because of drawing lines of sight from the different parts of the sun. If the sun were a perfect dot, then you would have a umbra, the darkest part, that would just extend in a cone out forever. Okay? But because it's extended, you don't get that. So we have a penumbra, And we have an umbra, and apologies for the choice on color there if you can't see that. But. Okay, what does this have to do with eclipses? Well, now the Earth happens to be just far enough away from the moon that the umbra just barely touches the Earth. That's a total eclipse. If it is even a little bit further away, you get an annular eclipse. That's it. That's all there is to it, okay? So what would you then end up seeing? You would see some light from this side and some light from this side. And if you turn that into a three-dimensional thing instead of a two-dimensional thing on the plot here, you get a ring of light, or an annulus. And there you go. Now you've got an annular eclipse, okay? And I think it's valuable to think about, yes, you can learn the basics of annular eclipses, or when the moon's a little further away from the Earth and so it doesn't completely block the surface, but why would that make it a ring? I think it's valuable to think about drawing lines of sight from parts of the sun to the Earth to see what that shadow looks like. And there's something cool about this dark shadow just not quite touching the surface of the Earth. So that leads us to some images. This is from Fred Espenek's website. He is rightfully called Mr. Eclipse. If I were to ever need to know anything, that would be where I would go. If there was another source, or if there was a question, I would trust Fred Espenek. So lunar eclipses here. This would be a penumbral lunar eclipse. As you see there, it's a little hard to tell that anything is happening at all. Penumbral eclipses are very, very subtle. That, of course, is when the moon is moving through what? The shadow of the Earth, but the shadow of the Earth that's still getting some light from the sun, right? Okay. Partial lunar eclipse is when the moon moves through the dark part of the eclipse, that umbra, but not all of the moon moves through it. Again, there's just a lot of geometry happening, a lot more than I've been able to go into, so that's why you get lots of different versions. A total lunar eclipse, the moon gets very, very dim and also gets very red. Does anyone know why it gets red? What color is the sky? Blue. What color is the light from the sun? White, right? How do you get blue from white? Take out the red, right? Or getting red from white, you take out the blue, right? Is really what I meant to say. Is that right? I'm sorry, I should have let you answer. You knew the answer. I think I'm just trying to make sure I get done on time. All right, so this is actually light filtered by the Earth's atmosphere, because the atmosphere tends to scatter blue more than it scatters red, and so the red light can go on a more straight direction to get towards the moon. So types of solar eclipses, we have a partial, we have an annular, and we have a total. We've discussed what these are, of course. A partial is sadly what we will experience here, meaning that some part of the photosphere's light will be getting directly to the Earth. Do not look at it if you like your vision. Annular is, again, we get some light from the photosphere coming around the edge of the moon, because the moon's orbit is a little bit elliptical, meaning that on some parts of its orbit it's farther away. That makes its angular size smaller, and that makes it not quite cover the surface. Or it means that it's a little bit farther, and so that shadow, that umbra, doesn't quite touch the Earth. Two different ways to think about it. So we got the total here, of course, in which you get to see that glorious corona. So for safety, if the photosphere of the sun is at all visible, you must wear eclipse glasses, not sunglasses. Sunglasses that have UV filter are not enough. Several sunglasses stacked together are not enough. Get the real glasses. We have some to give away today. There is a way of using welding glass to do it. Please double check. I'm not going to trust myself to remember the number that you need. Double check NASA's website. It has information about how to do that as well. The only time it is safe to look at an eclipse without eclipse glasses is when no direct sunlight is coming toward you. Here are a few resources you may not know, but a friend of mine from the south end of this data at a planetarium there, did a whole lot of work to actually get them to read a resolution about the 2024 eclipse and put a little bit of money to grants as well. So the state is supporting some work on events and other things. Let's see, also if you were looking at places to go, the Department of Natural Resources does have a website giving you specific advice. I don't know the state well enough to tell you where to go, but that's where you can go for that as well. And as I mentioned earlier, timeanddate.com. If you really want to get into the complexity, this is called the Saros cycle. It is a way of looking at eclipses that Babylonians actually used to realize that eclipses were predictable. And I have a very good friend that is a religion PhD, and he studies these things, and he said that basically when they realized that they could predict the motion of their gods, because the sun and the moon were literal gods, that kind of broke their religion. They had to rethink what it meant for the motion of the gods to not be at their own whim, but to be something that you could predict. And I think that's really exciting. And hopefully, maybe I'll put together a talk about this in more detail in the future. But that's what I have to say to you today. And hopefully that was at least a little informative. And I hope you're excited about the eclipses as well. Does anyone have any questions? Yes.
So we just had the supermoon, which my understanding was when the moon is at its perigee, the closest to the Earth.
That's right.
So that was just last few weeks ago, correct? 29th, I think. So now the Earth, the moon's orbit will be such so that just a month later it's going to be at its apogee. Is that why we're having the annular?
That's exactly right. Yep. So the question was just about 2 weeks ago. Note that that's about a half a month, right? It was on the closest part of its orbit because it's an ellipse, which means that it has a close side and a far side, and it moved the 2 weeks to the far side, and now we're having an annular eclipse because it's on the it's farther away than it might otherwise be. I'm not going to say it's farthest away because I don't know if it's exactly farthest, but other questions? Yes?
For the lunar eclipse that looks red, does it look red because it's on the very edge of that umbra? Like, why isn't it totally blacked out?
So the question is, why isn't a lunar eclipse totally blacked out? Because there is still, so the atmosphere of the Earth kind of acts like a lens to the light of the sun, and also a diffuser of the light of the sun. So some of the light that is hitting the Earth can actually bounce through the atmosphere. So there's like a ring of light kind of glowing. Does that make sense? Kind of coming around. Now, I usually, when I watch, the times that I've watched a lunar eclipse, there's a very reddish period and then a very dark period if it's a deep eclipse. So I think that was kind of in the reddish region, right? But that's my experience of watching them. I haven't done any real math on exactly how dark it gets. Does that make sense? But it is because so in fact, if you look at the Earth, technically more than half of it is lit by the sun because that atmosphere scatters a little light farther on what would be dark side. And if you're living in that spot, you call it twilight, right? So, other questions? Yes.
Do you know what else will be in the sky on April 8th? What else we should be looking at?
What else will be in the sky on April 8th? I don't, but I know how to find out, and I was hoping to show you this today, so you gave me an excuse. This is a tool called Stellarium, but this is the web version. If you have heard of Stellarium before, it's a big clunky thing that takes a lot of download. They have a web version now, which I actually think is easier to use. So we can, over here, just type in April is 4. Will it let me type? It might be easier. No, we want to go forward, not backwards. 4, 8. There it is. So if we zoom in here, we have Mars off to the right, which if you're in totality, you might get the chance to see. Oh, you can't see my pointer on the screen. So this is a little hard to see, but this is Mars right here. We've got Venus right there. We've got Jupiter over here. If you are in totality, you may get to see those when the sun is up, which is pretty cool. So those are a few things that you might see as well. Does that answer the question? Highly recommend tools like timeanddate.com and Stellarium Web there. They are pretty easy to use, and you can get a lot of questions answered about what's happening. There's a search bar over here where you can highlight, like if you're interested in a constellation, you can type that name in there. Also not sponsored. I don't have any relationship with any of these two tools. I just think they're useful. Any other questions? Yes.
Every planet that has moons has some form of eclipse but they might be a really big planet with a small moon, or the moon might be really close as opposed to far away. Is that right?
So every planet with moons would have some sort of eclipses. That's the question. So as long as that eclipse is close enough to their ecliptic that it can project its shadow onto their surface. Okay, so yes, we see eclipses on other planets. Jupiter, of course, is gigantic and has a whole lot of moons. So we see eclipses happen on Jupiter all the time. We basically see the shadow of the moon move across the planet's surface. So that can be seen. It's not uncommon in the planetarium. I will fly people to Jupiter and we'll happen to see an eclipse happen while we're there. So I don't plan it, it just happens. Okay, I think that is plenty of time. I will be up at the front if anybody wants to continue to ask me questions. Thank you very, very much. I hope that that was helpful and informative, and keep in mind that the model I just taught you works for other planets as well, which is why I teach things in terms of models instead of facts, so you can also understand, and for bonus points, go look up how to understand Venus's phases and why they were such a big deal to Galileo, and why they were a huge part of helping us understand that Copernicus was right. And this model of phases should help you do that. Okay, thank you very much.
All right, well, thank you. I feel better prepared, although I think I need to review. Let's see, how do I get back to the
you
slides?
need back to your slides.
I do. So I just wanted to give a little bit of a sneak preview for things that are coming up.
So you want to go back to the...
Nope.
Ah, there you go.
So actually, let me go to here. So coming up October 23rd, this actually isn't part of this series, but on the Notre Dame campus, there will be a Nobel Prize. So Thomas Suthoff, who won the 2013 Nobel Prize for figuring out how neurons communicate with each other in the brain. So super cool. And it'll be at 5 p.m., so October 23rd. That's in the Duncan Student Center. There are flyers outside, so you can pick up a solar eclipse glasses, get ready for next week, and then 2 weeks later, you can go to this cool talk. But it's also nice foreshadowing, for the Nobel Prize. So on November 8th, we will be having a panel discussion. And this week, I don't know if you're paying attention, who knows what Nobel Prizes have been announced yet? Go for it. Physics. So today was physics. Yesterday was. It was physiology and medicine. We're waiting on chemistry. There's actually 6. But anyway, this panel discussion will be about the physics prize, the chemistry prize, and then the physiology and medicine prize. So that's going to be November 8th. And it'll be faculty that have expertise in that area that will talk a little bit about the science behind those prizes and why they got them. So why is it interesting information? Why is it considered so important? So that's coming up November 8th. And then I also wanted to, so December 5th, we'll be having our first music talk. So Ryan Olivier, who's in the Department of Music at IU South Bend, will be talking about how he's a composer and how he creates sounds with geometry. So that is coming up. And with that, if you want to get on the mailing list, if you go to nduniverse.org, you can sign up and get reminders of when these talks are coming up. And thank you so much for coming tonight.